All right, welcome everybody. Today is the final lecture of GC in our sixth Geometry Topology seminar and Geometry Topology summer school. And thank you very much, and you can start.
Okay, well, thanks and welcome back. Yeah, so this is lecture 4. We'll be talking about, we'll continue talking about holomorphic curves in Nearly-Kahler 6 manifolds, but this time we're going to be looking at holomorphic curves with boundary. So this forms part of the larger subject of free boundary minimal surfaces, and we'll go a little bit into that, though frankly, I'm not an expert on free boundary minimal surfaces. I'll just tell you what it is that I know. Okay, so this will be a research talk, just like the previous one, but in a certain sense, this lecture might even be the most down to earth, perhaps. So I'm going to discuss 2 different free boundary problems for holomorphic curves in the 6th sphere. So the first is the classical, what I'm going to call the classical free boundary problem, and it's sort of a Riemannian geometry style problem. And so the setup basically is that you have a minimal surface, so 2-dimensional, let's say for this talk, you have a 2-dimensional surface, minimal surface inside a geodesic ball of some Riemannian manifold. Maybe the geodesic ball could be just the ordinary ball in Euclidean space. And you require that the minimal surface intersect the boundary of the ball orthogonally. Okay, this turns out to be not only a very geometrically natural condition, but it's very well behaved. And this subject of, what can you say about these so-called free boundary minimal surfaces, this subject has really just exploded in the last 10 years, kind of really around 2010, 2011. Since then, there have just been this huge amount of results and a huge amount of work just suddenly being done on this problem. And I'll mention that there's various questions you can ask, questions about existence and uniqueness and the Morse index. In this part, I'll just summarize a few of the existence results that are known, just to give a sense that there really are many free boundary minimal surfaces in the 3-ball in R3, for example. Then I want to turn our attention to uniqueness, right? In certain settings, you'd like to be able to classify all of the free boundary minimal surfaces of a given type. Okay, maybe with a given topology or maybe of a certain geometric class. So there's a very nice theorem of Fraser and Schoen in 2015, and they proved a very strong uniqueness theorem for free boundary minimal disks. And their theorem applies in not just Euclidean space, but also the round sphere, round end spheres, and also hyperbolic space. And personally, when I see a result that holds in all 3 space forms, okay, 0 curvature, positive, and negative, I immediately say, well, that's odd, right? That's a little strange when you have a minimal surface result that works in all 3 real space forms. Can you push this further? So a natural question is, is there a similar type of uniqueness theorem in, let's say, CP2 or CH2? Okay, and I'll discuss 2 different uniqueness theorems. Sort of one is due to myself, and the other is independently due to a group of folks, Li, Wang, and Ong. And we get slightly different results, but very similar. I'll compare and contrast in CP2 and CH2. And the point is that the method of uniqueness is very similar to that used by Fraser and Schoen. And so, inspired by this, you can continue asking for uniqueness results. And in particular, you might hope for a uniqueness result for free boundary holomorphic curves in a geodesic ball of the 6th sphere. And we get such a uniqueness result, and so we'll discuss it. But the point I want to make is that, all 3 of these theorems are proved in the same way. Okay, they use sort of Hopf differential type arguments. So this is sort of a Riemannian problem, and in the second part of the talk, sort of completely differently, I want to discuss a free boundary problem that's inspired by symplectic geometry. Namely, I want to consider holomorphic curves in some almost Hermitian manifold. Usually you look at a Kahler manifold, but it doesn't have to be Kahler. So you look at holomorphic curves in some almost Hermitian 2n manifold, and you require that the holomorphic curves have boundary in a fixed Lagrangian. Okay, and again, this turns out to be a very natural geometric problem, and it also is very well behaved analytically. And it's very important in symplectic geometry and for the study of invariance. In symplectic geometry, folks study holomorphic disks with boundary on a Lagrangian, and somehow the space of holomorphic disks with boundary on a Lagrangian gives you information about the symplectic manifold. Okay, now, I'm not a symplectic geometer, so I can't really say much more than that, but I know that there's a lot of work done on this problem in the symplectic setting. And rather than discuss existence and uniqueness, I want to discuss instead a sort of a different question, which is what can you say about the Morse index of such things? And I'm going to describe a general method, relatively general anyway, that goes back to Jim Simons, that uses complex analytic techniques, or really holomorphic techniques, to get Morse index bounds. And using those techniques, not only can you get Jim Simons' 1968 result, but you can also get a more recent result of Chen and Fraser on the Morse index bounds for minimal disks in the Kahler CPN. And it turns out that their proof doesn't just work in the Kahler CPN, it also works more or less, surprisingly, in the round 6 sphere, which is very much not Kahler, right? It's a strict Nearly-Kahler 6 manifold. And more generally, it works in other strict Nearly-Kahler 6 manifolds as well. So you can sort of get these Morse index bounds by using this general method, which I'll describe. And maybe since we have some time, I'll actually go a little bit into the proof. So we'll actually get to see this method in action. And then at the end, I'll mention some open problems. Okay, so let's start with the classical free boundary problem. So let M be a Riemannian manifold of dimension n. N will always be at least 3. You can think of M as, typically people take M to be Euclidean space with the flat metric. Let's let B be the closed geodesic ball, and S will be its boundary sphere. So that's a geodesic sphere. And what we want to study are immersed surfaces in the n ball whose boundary lies on the geodesic sphere. And we want to study variations of this surface, but we only allow for certain kinds of variations. Okay, these variations are called admissible, and they're the variations such that we continue to require that the boundary of the surface lies on the sphere. Okay, so we're sort of sliding the surface inside the ball, but in such a way that the boundary has to continue to lie on the sphere S. Okay, so these are the admissible variations. Okay, and given an admissible variation, we'll let X be its variation vector field. So you might ask, how does the surface area change under admissible variations? And there's a formula for this, known as the first variation of area. If you take the area of an admissible variation at time t, and you take the derivative at t equals 0, you get these two integrals, the sum on the right-hand side. So the first integral involves the mean curvature vector. Right, that's a normal vector, right? It vanishes precisely when your surface is minimal. And here you have a boundary integral, and this vector field nu here, this is the outer unit conormal. Okay, that's a fancy way of saying something very simple. It's just the unit vector field on the boundary of sigma, and it's just pointing outwards. Okay, so it's nu lives on the boundary. It's a vector field on the boundary of sigma, and it's orthogonal to the boundary, and it's the one that points outwards. It's unit length. So in particular, we might be interested in studying those immersed surfaces that are critical for all, that are critical for the area functional among all admissible variations. Okay, so such surfaces, if they're critical for the area for all admissible variations, that means that the left-hand side is 0. And that means it's 0 for all variations. So these are 0 for all x. And so that implies in particular that h, the mean curvature vector, is 0. And also that this inner product here has to be 0 as well. X has to be sort of tangent to s. So what this means, the vanishing of the second integral, that's equivalent to saying that u of sigma intersects, the intersection of u of sigma with s, that intersection has to be orthogonal. Okay, so we'll call such a surface, such a critical point among admissible variations, we'll call that a free boundary minimal surface. Okay, so a free boundary minimal surface is what you see here. It's, for us, immersed minimal surface. that's critical for all admissible variations. Okay, we're having a mini earthquake here, it seems. Lots of earthquakes. Okay, I have not gotten used to those. Equivalently, the mean curvature vector is 0, and the surface meets S orthogonally along the boundary. Okay, so the first condition, h equals 0, that's minimality. And the second condition is the free boundary condition. Okay, hence the term free boundary minimal surface. So questions you can ask are, for example, existence, right? What are some examples of free boundary minimal surfaces in a prescribed Riemannian manifold? Maybe you prescribe the topology. What sort of examples are there? The dual question to that is uniqueness. Can you classify the examples of a given type, right, with a given topology or something like that? And another question you can ask, which I won't address in this part, is that of the Jacobi spectrum. So can you say something about the Morse index? Can you classify those of lowest Morse index? Can you get some sort of bounds on the index or the nullity? Okay, we'll discuss that in the context of the other problem, the Lagrangian problem. But certainly there's been a lot of work done on the Morse index in this context as well, but that's not our focus today. So let me give you just a list of just a few examples. So let's let sigma gk be topologically the compact surface of genus G. G is at least 0, and it has k open disks removed. Okay, and k is going to be at least 1. So topologically, the simplest one is sigma 0, 1. That's a closed disk. Okay, so we have a trivial example. Okay, and let's just give some examples in R3. Let's just be really down to earth here. So the simplest example is the trivial one. This is the equatorial disk. Okay, so you just take the 3-ball and you intersect it with the plane z equals 0. That is a free boundary minimal surface where the topology is a disk. A more interesting example is the so-called critical catenoid. I'll give you a picture in a second. And the critical catenoid is a free boundary minimal annulus, and it's this one here, usually denoted K. And it's a particular one where this number alpha is approximately 0.46, and it's obtained by this formula where beta is the unique positive solution to this equation. Okay, and this was discovered by Nietzsche in 1985. And at the moment, at least, this is the only known free boundary minimal annulus in the 3-ball. Okay, so it's an open question as to whether there are any others. Okay, are there any other free boundary minimal annuli in the 3-ball besides this one? It's conjectured by a bunch of folks that this is the only embedded example. But at the moment, I don't think we even have any other immersed examples. So examples are hard to come by. Interestingly, though, just if you move to higher dimensional Euclidean spaces, so like R4 or something, then there are, in fact, free boundary minimal annuli. So that are not the critical catenoid. So there are, so in R4, there's plenty of free boundary minimal annuli. Okay, so the situation is quite different in higher codimension. Okay, this is a recent result of Feza and Sargent, who classified the circle invariant free boundary minimal annuli. They also looked at some free boundary minimal Mobius bands, which is a pretty interesting thing that can happen in higher dimensions. But here are some pictures. These pictures come from this lovely survey of Martin Lee. Maybe I'll put that in the official references, but he wrote this very nice survey on free boundary minimal surfaces, and it's just great. And so on the left here, you have in purple the equatorial disk, the trivial example. In the middle, you have the critical catenoid. And on the right, that's an example of a free boundary minimal surface with genus 0 and 8 boundary components. So that's sigma 0, 8 you're seeing over there. So there are, in fact, examples of free boundary minimal surfaces, sigma 0, 8. This is a theorem of Fraser and Shane, that there exist free boundary, embedded free boundary minimal surfaces, sigma of topology sigma 0k, so genus 0 and any number of boundary components. So then it's interesting to ask about what happens for a higher genus like genus 1. So there's a result by these folks which says that in genus 1, if there are sufficiently many boundary components, then such embedded free boundary minimal surfaces do exist if the number of boundary components is sufficiently high. In a similar direction, but sort of dual to this, it turns out that the genus can be made arbitrarily high if you assume only one boundary component. I believe this is Kapulius and Weigel, and I believe they used some sort of gluing and desingularization method. A similar result was proved independently by Kapulius and Lee using gluing techniques, and by Ketover using min-max theory. And they showed that there exist embedded free boundary minimal surfaces with 3 boundary components where the genus is sufficiently high. It's an open question, notice this is not addressed by the above, as to whether there exists a free boundary minimal surface of genus 1 and 1 boundary component. That's not known at the moment. Okay, so there's a lot more that's known beyond this. I'm really not an expert, but you can look at Martin Lee's survey, for example. All I want to point out is that there really are kind of, at this point, many different topologies that are known to exist. So there really are kind of lots of these things, at least in R3, and there's a lot of work done in higher dimensions as well, especially in codimension 1. So one thing we haven't seen so far is a free boundary minimal disk other than the trivial example. And it turns out there's a good reason for that. A theorem of Nietzsche in 85 showed that in the case when M is R3, there's only one free boundary minimal disk, and it's the trivial one. Suem showed in 97 that the same thing is true if you replace R3 with the round 3 sphere or hyperbolic 3 space. Of course, the analog of the equatorial disk is then a totally geodesic surface. These 2 results were then generalized further by Fraser and Chain. So if M is Rn, Sn, or Hn with their constant curvature metrics, then just in general, if you have a free boundary minimal 2 disk, then there's only one option. It has to be totally geodesic. So I want to go into this result because discuss the proof of this a little bit, because it was very motivating for my own work. And it has an interesting corollary, just by the way. It has a corollary that pertains to closed minimal surfaces in spheres. So let's let P be a totally geodesic n-1 sphere inside the n sphere. And let's let U be an immersed minimal 2 sphere, just topologically a minimal 2 sphere. And it intersects this n-1 sphere P transversely. And we're going to assume that U is invariant under reflection in P. So it's reflection invariant. Then it turns out that U of S2, your minimal 2 sphere has to be the totally geodesic 2 sphere. So roughly speaking, what this says is that reflection invariant minimal 2 spheres in Sn have to be the trivial one. Let's just see how the corollary follows from the theorem. So without loss of generality, let's let P be the intersection of Sn with this hyperplane here, xn plus 1 equals 0. Let's just take that one for simplicity. If U of S2 meets that hyperplane transversely, or the n-1 sphere transversely, then if you look at the half of it that lives in the upper hemisphere, the closed upper hemisphere, well, that's a free boundary minimal disk in the closed upper hemisphere. So by the uniqueness theorem, it has to be totally geodesic. So in the upper hemisphere, you have a totally geodesic disk. In the lower hemisphere, you have a totally geodesic disk. You put them together and you have this totally geodesic S2. And it's smooth because of the reflection invariance. Okay, so this is a very wonderful uniqueness result. And I think it's interesting to go into the ingredients of the proof, because it's actually, it's not a long proof. It's actually quite short. But it uses the assumption that M has constant sectional curvature very crucially. And it uses it in 2 places. So first, if you have a space form, a real space form, so a manifold with constant sectional curvature, and you have a minimal surface, let's say a minimal, well, here I have a disk, but this is true for any minimal surface, then on the minimal surface, there's this natural holomorphic quartic form, which I'm calling Q. I'm not going to go into details as to what Q is, but basically what it is you take the Hopf differential, that's a quadratic form, but it's vector valued, and you basically dot product the Hopf differential, this quadratic form, with itself, and that gives you Q. And the important thing is that this is a holomorphic object when you have a minimal surface in a real space form. Another interesting thing about sort of constant sectional curvature spaces that maybe we take for granted is that geodesic spheres are totally umbilic, right? So in other words, every tangent vector to the geodesic sphere is a eigenvector for the shape operator, right? The shape operator is just a multiple of the identity. Maybe that's a better way of saying it. Or equivalently, the second fundamental form of S is trace, sort of the opposite of being minimal, right? A minimal hypersurface is one for which the trace vanishes, but totally umbilic is the opposite, right? Your second fundamental form is only trace. It's the trace-free part which goes away, right? So this is something that we sort of are very familiar with in Euclidean space, but it's also true in Sn and Hn, but it's not generally true once you leave the realm of constant sectional curvature. It's sort of very weird, right? Geodesic spheres and other ambient spaces are not quite as symmetric, so to speak. So using these ingredients, here's roughly how the proof goes. So you introduce, Feza and Chang introduced polar coordinates, r(e) to the I theta on the disk. And there's an argument that shows that the free boundary condition, together with the holomorphicity and the definition of Q, and crucially, using the fact that geodesic spheres are totally umbilic, you can show that this quantity has to be 0 on the boundary. Okay, here partial z is what you think it is. It's partial x minus I partial y, and you take 1/2 of that. So this quantity is 0 on the boundary, and it turns out also that this quantity in and of itself is a holomorphic normal vector field. So if you have a holomorphic object that vanishes on the boundary, then it must vanish everywhere. So the second fundamental form of partial z must be 0. Now that by itself wouldn't force the second fundamental form to vanish, but the thing is that the surface is minimal. And so so if you couple this vanishing together with the trace of Roman numeral 2 vanishing, that does imply that the full second fundamental form vanishes. So your minimal surface must be totally geodesic. Okay, so this is sort of a complex geometric or a holomorphic argument. It uses this holomorphic quartic form and the Hopf differential pretty seriously. Still, despite the fact that this is very dependent on the constant sectional curvature assumption, if you're an optimist, you might hope for some sort of analogous theorem, maybe in CPN or CHN. And right, the difficulty is that Feza and Chang's proof certainly uses the constant sectional curvature assumption pretty seriously. But there's an interesting observation you can make, which is that there are nevertheless certain partial analogs of 1 and 2. So here they are. So on a minimal surface in, let's say, CPN or CHN, these are the complex space forms, there is a natural holomorphic cubic form. Okay, and this cubic form was discovered independently by Chern and Wolfson and Eels and Wood. And this holomorphic cubic form is sort of a different nature than the holomorphic quartic form Q, whereas Q basically is sort of purely a second fundamental form type of object. This holomorphic cubic form P relates not just to the second fundamental form, but also to what's known as the Kahler angle of your minimal surface. So basically, is your minimal surface a holomorphic curve? Is it sort of more like a Lagrangian? It relates to what's called the calibration angle or the Kahler angle. So it's not quite the same sort of information in this holomorphic cubic form. And moreover, the geodesic spheres in CPN and CHN, they're not completely terrible. They're not quite as symmetric, but in terms of their principal curvatures, they have 2 of them. So one of them has multiplicity 2n minus 2, and the other one has multiplicity 1. And you might think that that multiplicity 1 principal curvature maybe messes things up because you're not as symmetric, but actually that ends up being an important key. The geodesic spheres in CPN and CHN are what are known as Hopf hypersurfaces. And what that means is if you take the normal vector field to the surface, or to the hypersurface, and then you take J of that ends up being an eigenvector for the shape operator. That's a very sort of striking property. That's what it means to be a Hopf hypersurface in a complex manifold, I guess a Kahler manifold. And this eigenvector actually corresponds to this sort of asymmetric part. It corresponds to the multiplicity 1 principal curvature. So these are 2 observations that suggest that maybe there's some sort of modification of Feza and Chang's result to the setting of CPN and CHN. These 2 observations were made independently by Li Wang Ong and also myself around pretty much the same time. But we basically, both of us made those observations, but we came to slightly different conclusions. We use them in different ways. So there are these two theorems, neither of which implies the other. They're just different. So let's consider C2, CP2, or CH2 with their standard Kahler metrics. And Li Wang and Ong considered minimal Lagrangian disks in the four-ball of these things, okay? And the boundary of the disk lies on the boundary of the ball. And what they assumed was a very general boundary condition. This is actually more general in this context than the free boundary condition, right? The free boundary condition requires an orthogonal intersection of the disk with the sphere. Here, we're allowing the contact angle to, it doesn't have to be pi over 2, it doesn't have to be 90 degrees. The contact angle just has to be constant. Okay, but the boundary curve has to be Legendrian. And the Legendrian condition is very natural. It basically just means that your curve of intersection has to be orthogonal to psi. This is the Reeb vector field, for those of you who know your contact geometry. So it turns out that the free boundary condition is stronger than this. So this is a more general boundary condition even. And they deduce that U of D is totally geodesic. Okay, so this is a very nice uniqueness result, I think. So in my result, I allowed for arbitrary topologies. So any genus G and any number of boundary components, but I assumed a more restrictive boundary condition. I assumed the free boundary condition, which is contact angle pi over 2. And the conclusion is that if you have a free boundary minimal Lagrangian of any topology a priori, and it's free boundary in CP2 or CH2 or even C2, then in fact, G has to be 0 and K has to be 1. And your minimal Lagrangian a priori, which could have been really weird, there's only one option, it has to be totally geodesic. Okay, and the proof was, basically just, can you follow Fraser and Shane's arguments, but use these modifications 1' and 2'. So this shows that this, if you specialize to certain geometrically natural classes of free boundary minimal surfaces, maybe the situation could be quite rigid. Okay, maybe there aren't many options. So this suggests the question of, is there a similar uniqueness result for other geometrically natural classes of minimal surfaces, such as, for example, holomorphic curves in geodesic balls of S6. And so it turns out that by using pretty much the same methods, you get this result. Suppose you have a holomorphic curve in a geodesic ball of the 6th sphere. Okay, and the holomorphic curve is free boundary, so it intersects the boundary of the 6th ball orthogonally. And a priori, sigma has any genus and any number of boundary components. But in fact, the conclusion is that the genus has to be 0, the number of boundary components have to be 1, and your surface has to be totally geodesic. That's the conclusion. And the proof is the same. You essentially run Fraser-Shane's argument, but you actually have to do less work because the analog of Q, which is the analog of Q is this holomorphic section that I mentioned last time, this very abstract sort of quantity. It's abstract to define, but it's basically the second fundamental form dressed up in fancy language. It turns out that this is somehow, it plays very, very nicely with the holomorphic curve condition. So the proof is somehow even shorter. You don't even have to work quite as hard. Okay, but it's basically the same as Fraser and Shane's proof, just easier. So this has a very interesting corollary, just as Fraser and Shane got their corollary about closed minimal 2 spheres in the N sphere. So too, we can sort of play the same game and get an analogous corollary. So let's let P be a totally geodesic 5 sphere in the round 6 sphere. And suppose you have a, this time closed, connected orientable surface of any genus. If you have a holomorphic curve of that topological type, genus closed, connected, genus G into S6, and if it's reflection invariant under P, and it intersects P transversely, then in fact, your genus has to be 0, and U of sigma must be the totally geodesic 2 sphere. Okay, so this is a rigidity result for reflection invariant closed holomorphic curves in the round 6 sphere. And because holomorphic curves in the 6 sphere are the links of associative cones in R7, this implies, I'm not going to write it down here, it's in the paper, but this implies a directly analogous rigidity result for reflection invariant associative cones in R7. Right, so basically a reflection invariant associative cone, you have to say what you mean by reflection invariant, but a reflection invariant associative cone in R7 has to be 3-plane. That's the sort of G2 geometric corollary of all this. Okay, so that's what I wanted to say in the sort of classical free boundary case. Okay, I now want to move on to a sort of very different free boundary problem that's of interest to symplectic geometry. So this is the Lagrangian problem. So let's just begin with a very general setup. M will be any almost Hermitian 2n manifold. 2n has to be at least 4 for this to be interesting and sensible. And L will be a Lagrangian. Okay, so that's a half-dimensional submanifold, and we're fixing it in advance. And what we want to do is study those compact immersed surfaces whose boundary lies on the Lagrangian. Okay, so one thing that's interesting is that if U is a holomorphic curve, then the intersection with L is automatically orthogonal. Okay, this is just direct from, this is like a one-line argument directly from the definition of holomorphic curve and Lagrangian. This is maybe a nice exercise, in fact. So in a sense, so if you have a holomorphic curve with boundary and a Lagrangian, you automatically get the free boundary part of free boundary minimal surface automatically, right? The free boundary part comes for free. Do you get the minimal part? Do you get the other half of the definition? That depends on the context you're in. That depends on the nature of J and omega as to whether your holomorphic curves are minimal surfaces. Now, typically, this problem of holomorphic curves with boundary on a Lagrangian, that's typically studied in symplectic geometry, or Kahler geometry, I guess, almost Kahler geometry, really. And in that setting, omega is closed. You have an almost Kahler manifold. And if omega is closed, then omega is a calibration. So holomorphic curves are calibrated submanifolds, so they're homologically area minimizing, and consequently, they are definitely minimal surfaces. So the point is that in this setting, if omega is closed, then holomorphic curves with boundary and a Lagrangian, those are automatically minimal, and their intersection with L is orthogonal, so they are free boundary minimal surfaces. But there's another setting in which holomorphic curves are minimal automatically, and that's the setting where M is a Nearly-Kahler 6 manifold. This might be true for higher dimensional Nearly-Kahler manifolds, but frankly, I don't know. I'm really only, I'm primarily familiar with dimension 6. It's the minimality is definitely known. I think it's in Alfred Gray's 65 PhD thesis, but I don't remember. So I'm just going to stick to dimension 6. So in the Nearly-Kahler 6 manifold setting, then even though omega is not necessarily closed, right? It's closed if you're Kahler, but if you're strictly Nearly-Kahler, then omega is not closed. Despite this, as we saw in lecture 2, holomorphic curves in M6 are nevertheless minimal surfaces. So once again, you get this, they're free boundary minimal surfaces under this condition. An interesting thing is, and this is, I mean, I continue to believe that this is sort of odd. If M is strictly Nearly-Kahler, that's our case of interest. So in other words, Nearly-Kahler, but not actually Kahler, then the Lagrangian L, that's minimal too. It's very strange. So the Lagrangians in Nearly-Kahler manifolds are somehow much more rigid than in the symplectic setting almost. It's a little odd. So anyway, the problem is to study holomorphic curves whose boundary lie in a fixed Lagrangian L. And so by problem, I mean, well, there's many questions you can ask, right? You can ask about existence, you can ask about uniqueness, just like we did in the previous part, or you can ask about stability, right? So that is questions about the Morse index, the nullity, or more generally about the Jacobi spectrum. And I want to focus on the Morse index, since that's what I happen to know about. I don't really know much about existence and uniqueness in the symplectic setting. In the Nearly-Kahler setting, I think it's completely open. I don't really think anything is known about existence or uniqueness in the Nearly-Kahler setting, at least as far as I know. So I want to describe a very general method, well, a fairly general method. It's nice when it works. A method for getting a Morse index bound for minimal surfaces in even dimensional Riemannian manifolds. This method goes all the way back to Jim Simons. Maybe you can actually do it in odd dimensional Riemannian manifolds as well, but well, I would need to think about that. Let's just stick to even dimensional Riemannian manifolds anyway. So let's say you have an even dimensional Riemannian manifold. M nabla bar will be its Levi-Civita connection. R bar will be its curvature tensor. Fix a submanifold L. It's not necessarily Lagrangian, it's just some submanifold. And we want to look at compact-oriented minimal surfaces whose boundary lies in L. Just some notation. If you take the covariant derivative of a normal vector field, right, you'll get a tangential part and a normal part. The tangential part, that's the shape operator, or sometimes called the Weingarten operator. It's a tensor, and it's basically the second fundamental form, or the negative of it, related by this formula. And the normal part is the normal connection. Okay, so this is my notation for the normal connection. Okay, so as before, we want to vary our minimal surfaces such that we only look at variations such that the boundary of our surface, it has to stay in our fixed Lagrangian. So the sort of derivative of such a variation is going to be some normal vector field, and that normal vector field has to be tangent to L along the submanifold along the boundary. Okay, so this is what we'll call an admissible variation vector field. It's a normal vector field that along the boundary is tangent to L. And there's this classical formula, okay, that is the basis for considering the Morse index, right? If you have an admissible variation vector field eta, then the second derivative of the area functional at the variation vector field eta is given by this formula here. So notice that we have kind of this is a differential operator here, nabla perp. So this is a derivative, and these terms are zeroth order. Right, this is a tensor, and this is sort of another, well, it's a quadratic form, I guess. And so this is the extrinsic curvature. This is the shape operator, and this is the curvature of the ambient space. So we sort of saw this formula last lecture, but now because we're considering surfaces with boundary, we have this annoying boundary integral. Okay, and as before, we're using the notation that nu is the outer unit conormal, and E1, E2 is that will always mean a local oriented orthonormal frame for the tangent space. Here I'm summing over I from I equals 1 to 2. Okay, and so the Morse index basically is the number of admissible variations for which the second variation is negative, right? It's the number of directions you can vary such that the surface decreases its area, is area decreasing to second order. So how would you compute the Morse index? No one knows, it's really hard. So how would you estimate the Morse index? That's hard too, but here's sort of one general strategy that you might hope for. So this is a complex geometric or holomorphic method. So let's somehow, in some way, regard the normal bundle as a holomorphic vector bundle. Right? Remember that the surface sigma, the base sigma is a surface, and we're thinking of it as a Riemann surface. And some orientation and a metric. And so what you hope for is that once the normal bundle is a holomorphic vector bundle, you hope that the admissible variation vector fields that are holomorphic, so they're holomorphic sections, you hope that those are destabilizing. You hope that if you plug in a holomorphic normal vector field, you get a negative number here. Right? You hope that these are directions in which the surface decreases to second, the surface area decreases to second order. Now, if this is the case, then the Morse index is at least the number of independent holomorphic variation vector fields. And then hopefully you could use some index theorem, some index formula to compute or get some lower bound on this number. So that's the name of the game. So it's a three-step strategy. Step one is to rewrite the second variation formula in terms of holomorphic operators, so so-called Cauchy-Riemann or D-bar operators. Step two is show that this hope is really true. Show that if you plug in a holomorphic normal vector field, you really do get a vector field which is destabilizing, right? You get a negative number here. And then finally, use some like a T-Singer index formula or something to that effect, a Fredholm index formula to compute the Fredholm index, not the Morse index, the Fredholm index of partial bar. Okay, and so the conclusion will be that the Morse index is at least the number of holomorphic variation vector fields. This is the dimension of the kernel of partial bar, and the dimension of the kernel is at least its Fredholm index. Okay, so I'm going to use the full word index to mean Fredholm index, and just ind to mean the Morse index, right? Of course, these are completely different things. Okay, so that's the idea, but I want to go into just a little bit of the technical, just for 2 slides, the maybe some technical information. What more precisely, what is a D-bar operator, and what is the relevant index formula, you know, that would serve us well in doing step 3. So let's say you have a complex vector bundle E over a Riemann surface sigma. Okay, now a real connection is just my word for a connection on the underlying real vector bundle. So basically forget the complex structure on E. This sounds like a weird thing to do, but forget the complex structure on E, and just an ordinary covariant derivative operator, that's going to be called a real connection. The important point here is that we're not requiring that our real connection, nabla, we're not requiring that it preserve the complex structure. Okay, now, why would this be important? Well, this is important if you're working, let's say, in Nearly-Kahler geometry or some geometry that's not Kahler. Because if you're working in a geometry that's not Kahler, then the Levi-Civita connection does not preserve J. Right, so this is extremely important, sort of an extremely important generalization for when you're working with the Levi-Civita connection in non-Kahler manifolds. So let's let Hom minus denote the vector bundle, whose fibers are the JJ antilinear maps. That's just a notation. And so given a real connection nabla, you can define a corresponding D-bar operator, and it's basically the antilinear part of nabla. Okay, so this is sort of a standard thing that you would do in Kahler geometry when your connection is assumed to preserve J. Okay, but the point is that here nabla, you know, as I said many times, that doesn't necessarily preserve J. That's kind of the novelty here. Okay, so an operator of this form, D-bar nabla, the basically antilinear part of nabla, we're going to call that a real Cauchy-Riemann operator. Okay. And so the idea is to rewrite the second variation formula in terms of real Cauchy-Riemann operators. And it turns out that then you can compute the Fredholm index of such a thing by a generalization of the Riemann-Roch theorem. This is a generalization of the Riemann-Roch theorem in 2 respects. First, we're going to allow for the base sigma to have boundary. So we're going to have some boundary conditions. And second, again, we're allowing for these Cauchy-Riemann operators that arise from connections that don't necessarily preserve J. So that's a second way in which what we're going to say generalizes the classical Riemann-Roch theorem. So let's introduce the boundary condition first. So sigma will be a compact Riemann surface with boundary, and E is a complex vector bundle. Complex vector bundle of complex rank R. And let's let F be a totally real subbundle. And what that means is that each fiber is a totally real subspace. So that just means that J of the fiber doesn't intersect the fiber, right? Or it intersects only at 0. Right? So you can imagine that F is like a Lagrangian or something like that inside E, okay? Assuming that E has enough structure to define Lagrangian. This is sort of a complex version of Lagrangian, if you like. The boundary conditions we want to consider are the ones that are going to show up in the Lagrangian boundary problem. So given a Cauchy-Riemann operator D, let df be the restriction of D to the sections which fulfill the boundary condition. So these are the sections which on the boundary lie in this prescribed totally real subbundle, F. So the point is that given this formalism, we have this generalized Riemann-Roch theorem. So D is a real Cauchy-Riemann operator. For technical reasons, we need to assume it's this particular Sobolev class. Then the real Fredholm index is given by, well, this topological formula. Here, chi of sigma is the Euler characteristic of sigma, and mu of E comma F is a topological quantity known as the boundary Maslov index of the bundle pair EF. Right, this is a bundle pair, right? Because you have E, a complex vector bundle, and you've chosen in advance a totally real subbundle. So I'm not going to go into what this means. There's a nice discussion of this in McDuff and Salomon's book on J-holomorphic curves. But basically what this is it's a, you can think of it as sort of a bundle pair version for surfaces with boundary of the first Chern class, right? You want to basically say, what is the first Chern class of a complex vector bundle over a surface with boundary? But you also want to sort of study how the totally real subbundle kind of twists as you move, as you sort of go in a loop around the boundary. That's somehow what this is measuring. I understand this one, it's explained to me, but frankly, I'm not kind of fluent enough in the topology to be able to maybe give a satisfactory exposition of what mu of EF really measures. But what I do want to emphasize is that it's a topological quantity, and it is integer valued. And if F is trivial, it reduces to the 2 times the first Chern class of E. Right, so it really is kind of a generalization of the first Chern class. Certainly, that's what would be here if F weren't there, right? Just like in the classical Riemann-Roch formula. Okay, so what can you do with this technology? So using what I just said, you can get some topological Morse index bounds in various settings. So this was done by Jim Simons and recently, for example, by ChenFraser. So ChenFraser looked at CPN with its standard Fubini-Studi Kahler structure. Okay, so it has a constant holomorphic sectional curvature. L is an oriented Lagrangian, and they're considering minimal 2 disks. And so let's let, as they do, U be an immersed minimal 2 disk in CPN, and its boundary is going to lie in the Lagrangian fixed in advance. And we're going to require that we're not assuming U is holomorphic. So we have to assume from the outset that U meets D orthogonally. And we're going to assume that the intersection is positive. They define this positivity condition like so. It basically means it's sort of a convexity assumption, right? If L were not an oriented Lagrangian, but rather some sort of like a hypersurface, like a sphere of some sort, then this and your disk lied inside the interior of the sphere, then this positivity condition would hold. Okay, this is sort of saying that the curving, this is the second fundamental form of L here. The second fundamental form of L, like in the direction of JT, this curving is less than the curving of L in the direction of negative nu, where negative nu is the, what would you call it? The inward unit conormal. Okay. What I'd like to say otherwise is that this positivity condition, this is automatic if U is a holomorphic curve. Okay, if U is holomorphic curve, both sides are 0, or rather, what do I want to say? Sorry about that. When U is a holomorphic curve, you get equality. That's what I meant to say. Okay. So under these conditions, they show 2 things. So first of all, the stable minimal 2 disks with this with boundary on a Lagrangian that intersect the Lagrangian positively, the stable ones are precisely the holomorphic curves. Okay, so sort of the left direction is clear. It's the right direction that's really non-trivial. And second, if your minimal disk is unstable, then they're able to use the methods I just mentioned to get a very general topological bound on the Morse index. Okay. And I believe, if I'm reading their paper right, that maybe part B doesn't need the disk assumption so much. This n here maybe could be replaced with an n times the Euler characteristic, perhaps, if I understand that paper right. So maybe B is even slightly more general. Okay. So it would be nice to sort of have a similar statement in the round 6 sphere, and it might seem strange to say that the round 6 sphere is kind of like the Kahler CPN, but that's sort of my philosophy.
the round six sphere, despite definitely not being Kahler, is somehow kind of similar to the Fubini-Studi CPN. I'm deliberately vague about what I mean by that because it's just an intuition. Right. Yes, in the holomorphic curve case, yeah, you definitely get equality here. Sorry, I'm just second guessing myself. But this is definitely how that works. Yeah, that's how that works. Okay, sorry about that. So here's the setting of the result that I'm here to advertise. So if M is a strict Nearly-Kahler six manifold, so for instance, the round six sphere, or it could be the Nearly-Kahler CP3 or S3 cross S3. We saw some examples in the last lecture. And let's let L be a Lagrangian. And suppose sigma is a compact orientable surface with boundary, a priori any topology. And so let's let U be an immersed holomorphic curve with boundary in the Lagrangian. Then you can get this topological Morse index bound exactly as ChenFraser do. The Morse index is at least this boundary Maslov index, or boundary Maslov class. This theorem has several limitations, and I think it's important to understand these limitations. So in the edge case, where the boundary is empty, you might hope that this would imply some sort of nice Morse index bound for closed holomorphic curves in S6, for example, but that turns out not to be true, because when the boundary is empty, this number is 0. And saying that the Morse index is at least 0 is not very interesting. That's always true. Right? So this is vacuous if the boundary is empty. So that's a little disappointing. More significantly, and this is important, this number, this boundary Maslov index, is integer valued. And so in particular, it could be the case that it's negative. And certainly if you get a negative number here, then this is definitely useless. However, I don't know how often this happens. I am optimistic that this sort of thing does not happen very often, or at least maybe you get a negative number as often as you get a positive number would be kind of maybe the less optimistic conjecture. Nevertheless, it is my belief on faith that this number is probably positive a lot. I will come back to this point later. It would be nice to test what this number is on explicit pairs. Maybe just pick a holomorphic curve in a strict Nearly-Kahler six manifold, pick a Lagrangian, and suppose your holomorphic curve, its boundary lies in the Lagrangian L, and just compute what this is, and then you could see whether it's positive or not. The problem is that there are not many examples of these things. I mean, they surely exist. There are surely plenty of them, but examples are very hard to come by. And I think it would be important and interesting to construct actual examples of holomorphic curves in, let's say, S6 with boundary lying on a Lagrangian, maybe other than the completely trivial example. Okay, so that would be an interesting direction for further investigations. Okay, but how would you prove such a thing? You basically follow the 3 steps that I indicated. This is also more or less how Chen and Fraser's proof goes as well. So you look at the second variation of area formula, right? And you have kind of this differential operator term, and then you have these 0th order terms here. And the idea is to rewrite everything in terms of real Cauchy-Riemann operator. So for us, the real Cauchy-Riemann operator will be basically the antilinear part of the normal connection. Okay, and again, the important point is that the normal connection, because we're in a Nearly-Kahler manifold, strict Nearly-Kahler manifold doesn't preserve J. Okay, so D will be our sort of round D bar operator, if you like. And for notation's sake, alpha eta will be this one form. And what you can compute is this red term here, if you add on a normal curvature term, is equal to these, the sum of these 3 things. Notice that our Cauchy-Riemann operator D appears in the first 2 terms. That's good. And the 0th order terms, they're equal to this same exact normal curvature term minus 2 lambda squared normal beta squared. Here lambda, I neglected to mention, this is the type constant that appeared last lecture. It's sort of it depends on the scale. So you can sort of, if you dilate your M6, or scale by some homothenity, then you can arrange for lambda to be 1, for instance. It's just some positive constant. The point is that when you add these two equations together, of course, the normal curvature terms cancel. That's very nice. And then if you apply Stokes' theorem to d alpha eta, you get this second boundary term here. And here's what you end up getting. Okay, so this is sort of the suitable version of the second variation of area formula. And this applies to any holomorphic curve with boundary on any submanifold L. We haven't assumed Lagrangian yet. This applies to any holomorphic curve, sigma, with boundary on a fixed submanifold L in a strict Nearly-Kahler 6 manifold. So this is kind of a second variation of area formula that's quite general and possibly has further applications. But what's annoying us is this boundary integral, right? This boundary integral is a problem, and we need to deal with it somehow. And sort of a miracle is, I don't know if it's quite a miracle, but something that's very nice is that the triple of conditions, the trinity of conditions, Nearly-Kahler together with holomorphic curve, together with Lagrangian, those three together imply that the boundary term goes away. That's sort of very fortunate. So now we're going to assume that L is Lagrangian. And you're left with this very nice, very simple second variation formula. It's sort of very nice thing to work with. And you can see right away that if eta is holomorphic in the sense that it's in the kernel of D, well, if eta is in the kernel of D, then the first term disappears, second term disappears, and you're left with a negative number, assuming eta is not 0. So this shows that, as we hoped several slides ago, holomorphic admissible normal vector fields are in fact destabilizing. So all that's left is to apply Riemann-Roch, and we're done. It's sort of very short. So let's just prove theorem C. So to apply the generalized Riemann-Roch, we need to say what our totally real subbundle F is. And I mean, it's the thing which defines, it's basically the subbundle which defines the condition of admissibility. Right? So F is going to be the normal vector fields, or the normal vectors along the boundary that lie tangent to L. Okay, that is a totally real subbundle of the normal bundle. So this is our bundle pair here. This is our E and this is our F that we're going to apply our generalized Riemann-Roch theorem to. And what we've seen on the previous slide is that if eta is admissible, right, that means that eta satisfies this boundary condition, this totally real boundary condition. And if eta is in the kernel of D, so it's holomorphic, then it's destabilized. So the Morse index must be at least kind of the kernel, the dimension of the kernel. It must be at least the number of admissible holomorphic normal vector fields. So this is the dimension of the kernel of DF, and that's at least its Fredholm index. So now just apply the generalized Riemann-Roch theorem to compute the Fredholm index, and this is the number you get. But this is also a boundary Maslov index. It's the boundary Maslov index of the tangent bundle of sigma with respect to the tangent bundle of the boundary of sigma. And it turns out that the boundary Maslov index is additive. So when you add these two together, you get exactly this. Okay, so that's most of what I wanted to say, or pretty much everything. There are some obvious open questions due to the fact that this theorem C is unfortunately not quite satisfactory in some respects. So, for instance, when is the boundary Maslov index non-negative? This is probably true a lot of the time, but it would be good to know. There's a beautiful Chern-Weil formula for the boundary Maslov index due to Tommaso Piccini somewhat recently that may help. So just as you can compute, there's this, these wonderful Chern-Weil formulas for the Chern classes and for the Pontryagin classes and for the Euler class, Piccini has noticed that there's also a Chern-Weil formula, sort of an integral of some kind of curvature terms. There's such a formula for the boundary Maslov index, very general for a bundle pair. And it's possible that maybe in the case of the sixth sphere, you could, or some explicit case, you can, plug things into that formula and maybe compute and do some estimates and not hard estimates, but just basic estimates and sort of see what happens. It would also be very good to have explicit examples of these pairs. There ought to be, maybe not a huge number, but probably these should exist in some reasonable quantity. So it would be good to have examples of pairs of holomorphic curves in, let's say, the sixth sphere, whose boundary lie on a Lagrangian. And it would be good to, well, computing the Morse index is very hard, but certainly it would be good to compute this boundary Maslov index and sort of see what happens. Finally, nothing has been said about the nullity. We've just discussed the index, but it would also be good sort of just as a general question to discuss the nullity of these holomorphic curves with Lagrangian boundary. So I'll stop here, and thanks for your attention in all 4 lectures. I hope this has been interesting, and I hope you enjoy the other talks as well.
All right, thank you very much. Any questions? Oh, recording is stopped or
It's still going.
going?
We're still
Okay.
recording.
Oh, maybe I'm not. Yeah, right. So the host has changed. All right. Any question?
Do you want me to?
No, from chat. Okay. Thank you very much for very nice lecture series and wonderful lecture series. And we're gonna meet 2:30 in the afternoon. Somebody can finish the recording.